Okay, so we're talking about heaps. The idea behind a heap is super simple. It's just a tree where if you go to any node in the tree, it is bigger than either of its children. And that's pretty much it. So that means the largest item is going to be at the top. The second largest item is going to be in the second row. Not necessarily true that the third largest item goes here, right? It just is, it's considered a valid heap as long as every node's children are smaller than itself. There's probably a more formal definition of that somewhere in the text, and we may take a look at that later, but that's the basic idea. Okay, so basically what I want to talk about with heaps is the main operations that we need to work on are inserting something into the heap, removing something from the heap, and then after that we're going to talk about using a heap to sort an array. But before I do that, I want to just talk a little bit about how we would implement a heap in our code. So how we would represent a heap. And I went back and forth on this many times in the textbook. You know, he doesn't actually get to the representation until he's talked about heaps in a more abstract way for a long time. So if this doesn't make sense now, I'm only doing this because I think it might help make the abstract step we're about to do make more sense. So if it doesn't help, don't worry too much about it. We'll come back around to it again later. Please feel free to jump in anytime you have a question, either chat or voice is fine. So let me look at a binary tree and show you how we would, you know what, there's something else I need to tell you about heaps that I totally forgot. Heaps, another requirement for a tree to be a heap, first of all, it's binary. And the other requirement is that it has to be a complete binary tree. So you can see that this one is a complete binary tree. Just to review quickly, that just means that all of the levels are completely full except the bottom level. And the bottom level is filled up from left to right. That makes it super easy to represent a heap using an array. And so let me show you a picture of that. I'm going to have to change what I'm sharing. So this is just the text that you're seeing now. This is not a heap. But it is a complete binary tree. So what I'm showing you now is how you can use an array to very simply and efficiently store a complete binary tree. As long as you know it's always going to be complete, this works. Okay. So we just put the items into the array in the order that we see them, top down, left to right. So level 1 goes first, then level 2 left to right, Bob, Tom, then level 3 left to right, Alan, Alyssa, Nancy. Okay. The nice thing about this is that it's very easy to, so the root is always going to be at index 0. It's very easy to figure out the children or the parents of any particular node. So you can look down here. If the node has a left child, it's going to be at 2 times the index of that node plus 1. So Jane, 0 times 2 plus 1 is 1. So Jane's left child is Bob. 0 times 2 plus 2 is 2. So that gives us Jane's right child. Okay. And then just to take another example, let's look at Bob. Let's look at Tom. Okay, so Tom's index is 2. So Tom's left child is going to be 2 times 2 plus 1, which is 5, Nancy, right? Tom's right child is going to be 2 times I plus 2, so that's 6. Turns out there is no 6, so that means that Tom does not have a right child. And then Tom's parent is going to be 2 minus 1 divided by 2. 1 divided by 2 is 0. So Tom's parent is at index 0, so it's Jane. Okay, now having said all of that, I'm not actually too concerned that you memorize those formulas, or for this chapter, I'm not even going to expect you to be able to look at the code and understand it the way that I have in previous chapters. But I'm mostly just throwing that out there because I think it's so cool how you can store a complete binary tree in an array in this very simple way. Anybody want to ask a question about how the complete binary tree is going to be represented with the array? I could also show you another example if you think that would help, but unless someone requests it, I think I'm going to assume that we're okay with this for now. And we will see that again later. Okay, so back to the heap that we were looking at. Oops, I think I clicked the wrong thing. No. Oh, this is tiny. Okay. So you're seeing my heap now again, right, with the 45 at the top? I don't know why I have to ask that. I see the green outline, so I should know. Okay, so we're gonna use this example to talk about how something is inserted into a heap, and then we're going to talk about how something is removed from a heap. Okay, so the first thing, oh, sorry, I'm on the wrong slide. Okay, so this is the original heap. Well, it was supposed to be the original heap. And we are going to insert 42 into this heap. The way that works is we are going to insert it as the last item in the array, which means it's going to go down here as the next leaf on the bottom level, right? So that's one of the reasons I wanted to show you the implementation, is just that it's so easy to know where to put the 42, at least initially, because you just put it whatever the next empty spot in the array is. So we're going to put the 42 at the bottom level like that. Now, clearly, that's not the correct place for it. So what we're going to do now is we're just going to swap it upwards until it gets into the correct position. That is called, I've always heard it called re-heapify up. In the text, I think he calls it trickle up, something like that. So either of those terms is fine. But so we look at the node above the 42, it's smaller than 42. That tells us we need to swap them. So we swap the 42 and the 21. Then we look at the 42's parent again, and it's still smaller than the 42. So we need to swap those two nodes. Oop, wrong way. Okay, now we compare 42 with its parent, and 42 is now less than its parent. So it's in the right position, and we're done. We have inserted 42 into the heap. Any questions about that? Okay. I just have to say, I think the whole heap idea is so cool. I'm glad we are talking about it. It's so, I mean, I think it's really easy to look at and understand what's going on. And it actually turns out to be also very efficient. Okay, so that's how we insert something into a heap. the way we remove something from the heap is that when we have a heap, we always remove the top item from the heap, or in other words, the root. Okay, so in a heap data structure, you don't remove things from inside the heap somewhere. You always just remove the root. Okay. The biggest place where you're going to see heaps used is as the implementation of priority queue, right? We talked about priority queue earlier in the semester. You did an assignment where you had to use a priority queue. You probably had no idea what it looked like behind the scenes, right? But this is what it looked like behind the scenes. Every time you had to, and I can't remember what the function is, but when you have a variable of type priority queue and you want to add something to the priority queue, I can't remember if it's insert or add or whatever, but what we just did is how that worked behind the scenes. And then when you remove something from a priority queue, you always remove the item with the highest priority, right? So that exactly matches what we're doing here with the heap. We just remove an item from the heap, and that's going to be the item with the highest value. Okay. So I hope that makes sense about the fact that it's a great data structure to implement a priority queue. Okay, so how do we remove something from the heap? Here's what we're going to do. This leaf, the 21, is going to have to go away, right? Because when we're done, it's going to have all three of these levels filled, and then the first two slots of the bottom level filled. So this leaf is going to go away. So what we're going to do is we're just going to put the 21 up here at the root. And then in the implementation, you can imagine that there's a num items variable, and we're just going to say num items minus minus, and that's going to make it so that conceptually this node here, the 21, goes away, right? When we say num items minus one, num items minus minus. Okay, so we put the 21 at the top, we move the 21 to the top. Here's what it looks like before the move. There's what it looked like after the move, okay? We just moved the 21 to the top. Sorry, it took like 4 screens or whatever to do that. Any questions about what we just did? Obviously, now the 21 is in the wrong place, right? So now what we're going to do is we're going to re-heapify down. In the textbook, he calls it trickle down. So what that means is we are going to look at, we're going to swap the 21 with the largest of its two children, unless it's already in the right position, right? So if the 21 is less than either of its children, we're going to swap it with the bigger of the two children. Okay, so we're going to swap the 21 with the 42. Okay, now at least one of 21's children is still bigger than the 21. So we're going to do the same thing again. We're going to swap the 21 with its bigger child, which is the 35. So swap the 21 and the 35. And now we're back to having a heap again. Okay, we've got the largest item at the top. All of the nodes have children that are less than themselves. So that's removing something from a heap. And that's pretty much all there is to that. So look at this. I said there were 3 things we're going to have to do. We're going to have to insert, remove, and sort. And we've already done 2 of them. So we're doing well. Any questions? Okay, let me just say that you're also going to need to be able to, so this is sometimes called a max heap. That's just if in the particular context that we're talking in, there's a reason why we need to differentiate between a max heap and a min heap. Normally we would just call it a heap. And the assumption is that it's a max heap, max meaning that the max item is at the top. A min heap is just the same thing except reversed, right? The smallest item at the top, each node in the tree is smaller than both of its children. And then everything that we do in all those operations, we just have to reverse bigger than instead of less than, and less than instead of bigger than. Okay. So we'll have a chance to take a look at that in a minute. All right. So if there's no questions about that, that's sort of like my basic, before we even get started, introduction to heaps. And really, I have to say that's, we've covered like, I don't know, 3/4 of it, of what you need to know already. All right, what I want to do now is I'm just going to go through the chapter. I actually thought about using the PowerPoint slides that the publisher provides, but the PowerPoint slides are really just screenshots of the text anyway. So I decided to go with the text. So let me share the text instead. Okay, so in a lot of ways, it's going to follow the same pattern that he has with all the other data structures. Here's the formal definition, right? Contains a value greater than or equal to the, so let's see, a heap is a complete binary tree that is either empty or whose root contains a value greater than or equal to the value in each of its children and has heaps as its subtrees. Okay, so I think that's just another way of saying it the way I said it. So here's an example of a heap. Here's an example of a min heap. Any questions about that?
On the min heap, wouldn't you want the lowest value on the left side?
On the left side.
So if we're looking at example B on the bottom, level 3, 9, 6, 10, wouldn't it?
So that's a great question, and the answer is no. It does not matter what order things are at any level.
Oh, wait, no, you're right. Okay.
Okay. So
yeah, because I see on A it's the same. Okay.
Yeah. I don't know if the example we were looking at just accidentally followed that rule, but it does for each.
Actually.
Yeah, okay. I mean, it does for each pair of siblings. It did, but not all the way across any particular level. So anyway, the bottom line is the order of the nodes in a particular level does not matter. So, and a heap is fairly limited, right? So it's not like you can use the heap to, like with a binary search tree, once you've got a valid binary search tree, it's very easy to just go through and print everything in order, right? Or find the smallest item. In a heap, there's really no easy way to print the items out in order, find the smallest item, anything like that. It's just specially designed for the situation where, for priority queue, basically, right? The situation where the only thing you ever want to remove is the largest item. So you place in the next open space then. Yes, whenever you insert something, you always just place it in the next open space and then reheapify up, right? So right now, if we wanted, looking at A, if we wanted to insert, I don't know, 8 into the heap, we would put it down here as 6's right child. And then we would reheapify up, which would mean we'd have to swap the 8 with the 6. And so the 6 would be at the bottom and the 8 would be on this second level. Okay, so the answer, so the question was, do you place things in the next open space? The answer is yes, but I just want to clarify that you place it there and then you have to reheapify up to make it so that what you have is still a heap. Does min heap have different arithmetic than max heap? It's exactly the same, except you're always just going to replace less than and greater than. You're just going to reverse them. Okay, so heap operations, I'm not too worried about these. You know, there's the usual, see if it's empty, see how many nodes there are, get the height. The only ones we're really concerned about are, well, so get the item in the heaps root. That's different from removing it, right? So there's going to be one operation that just returns the root. And then there's going to be a second operation that removes the root. But here's the two important ones that we just went over, right? Insert a new item into the heap and remove an item from the heap's root. Remove the item in the heap's root. Okay, and so in this particular chapter, I'm not going to hold you responsible for the code. So we're going to kind of breeze through some of this stuff. This is just the UML diagram for exactly what he listed up there. Now, just like he does in every chapter, we're going to do the description of the abstract data type with all of the comments. And then we're going to have an interface with all the comments. And, you know, I'm really glad he does all of this, right? This is a very formal way of presenting material, and I think it's useful. In our particular case, we're not going to be too worried about all of the details. Okay, and here's a good point, okay? We've also been talking about an area of your computer's memory called a heap. Don't get that confused with what we're talking about now. They're just two completely different things. They're both called heap, but don't try to make some sort of a connection between them, okay? Okay, now he's finally going to start talking about how to implement a heap. And here's where we get that picture that I showed you before. Let me know if you have any questions or want me to talk about this again. We talked about the left child and the right child and the parent. Okay, I already told you about this. This is about how to, well, so retrieving an item from the heap is easy. You just return the root, right? So there's the code for the function that gets the top item in the heap. Or the, yeah. So removing an item from a heap, that's what we talked about before, right? I already showed you, you num items minus, or so in this case, item count minus, right? You move the last item in the heap to the root, and then item count minus, and then reheapify down, right? And I actually think the way I explained it may be a little simpler than what he's doing here, but let's just note that this is the same thing, okay? We're going to delete the 10. So what he does is he shows it as disjoint heaps first, and then he shows it as a new heap with the last item at the top. I'm not really sure what the point of it is of having this intermediate step here, but then he shows, he calls it trickle down by swapping. So the 5 gets swapped with its larger child, and I call that reheapify down. Any questions about this diagram? It's basically repeating what we did already. So if it's not clear, then we definitely should stop it and get it worked out. You always take the last one, yes. Right? And that's why it's so easy, because I just say item count minus, that automatically makes it so that the last item in the array is no longer considered part of the heap. Right? If just to make a random observation that may help you understand what's going on here, or may confirm that you understand what's going on here. If all I wanted to do was remove the 5 from this heap, what would I do? What would be the code for that? One statement, one very simple statement. All right, is this? Yes, that's exactly right. Item count minus minus. Everyone understand that? Because these are all being stored in an array. If I just say item count minus minus, that means that this last item is no longer considered part of the heap. I think we've had similar situations to that already, right? I mean, I think we've had, you know, like in the Q example, if we said back minus minus, that was how we removed an item from the back of the queue, right? Same thing here. The way we remove an item from the back of the heap is just item count minus minus. The only difference here is that we're actually trying to remove the root, and the way we do that is we remove the last item and we put it at the root. Okay, so he talks about this thing called a semi-heap, which I haven't actually heard that term before, but the author of this text has a name for this situation where in this picture here, the whole thing isn't a heap, but both of the subtrees are heaps. And so in that situation, it means that all you have to do is reheapify down and you'll be back to having a heap again. Okay, so this heap rebuild function is just doing that. It's just reheapifying down. And he's doing it using recursion, I think. Yeah, here's the recursive call. I actually think that this should probably be done just iteratively. Just use a while loop. Easier, simpler, and more efficient, but that's what he does. But don't worry too much about this code. I'm not holding you responsible for the code. Just know that this function is, another word for this function would be reheapify down. Okay. This is the same example again, except this time it comes with array representations at each step, right? So here's the original heap. So this is the array that represents this heap. Stare at that for a minute. Tell me if that does not make sense. It's going 10, 9, 6, 3, 2, 5, right? And then this is the representation of the heap once we have moved the 5 to the top. And again, that just means we did item count minus minus, right? I guess if I was drawing this picture, I would want to actually put garbage values in all of these and also keep track of item count, because that's actually what's happening, right? The reason these are blank down here is because item count is 5, and there's our 5 items. Okay, and then reheapify down is just, I'm going to swap the 9 and the 5, swap the 9 and the 5 in the array. Done. Any questions about that figure? Okay. Well, we're still on remove. So we could talk a little bit about the efficiency of remove. Hopefully at this point, it'll be fairly intuitive, but that's log in, log base 2 of n, right? Or just big O would be log in. Just because the most swaps we're going to have to do is the height of the tree, right? And the height of the tree is log n. Okay, so my guess is that if you're comfortable with big O of log n, that probably makes total sense. If you're not comfortable yet with big O of log n, then nothing I say right now is probably going to make that clearer unless we go back and study that some more. So I'm gonna just leave that for now. Feel free to get in touch with me if you want to talk more about that. Okay, adding an item to a heap. We already talked about it, but let's just go over it again. We just put it at the bottom. So we're adding 15 to this heap. We put it at the bottom, and then we trickle it up. So swap the 15 and the 6, and then swap the 15 and the 9. Okay. Efficiency of insert is the same as remove. Okay, because we're just going up the tree swapping. So here's the implementation. This is the part that you really can just ignore. I'm not going to make you, I'm not holding you responsible for it. You might want to look it over just because it's so cool, right? But I'm not holding you responsible for it. Some method definitions. Okay, so here's something that actually is significant. Give me a second here. So one of the functions is called heap create. Actually, that's a private function that they're writing, but that's required because one of the constructors in the heap class accepts an array of integers as an argument and converts that array into a heap. So what the heap create function does is it takes an array that is just randomly placed numbers in there and rearranges the items in the array so that it's a heap. So in this example here, this is the original array. This is the heap that that array would represent. And so what we're going to do is basically this right here. Remember, heap rebuild means reheapify down. So what this is saying is start at the end, turn that into a heap, right? Well, none of these leaves, nothing's going to happen when we call reheapify on a leaf, right? So the first 3 times through this loop, nothing's going to change because 10 is already a heap if it's just by itself. 2 is already a heap if it's just by itself. 9 is already a heap if it's just by itself. So now we're on the 5. So we call heap rebuild on the 5. And what that does is it causes the 10 and the 5 to be swapped because the heap, remember the heap rebuild is what I'm calling heapify down, which is just going to swap the 10 and the 5. Okay, so now, so basically what we're doing is we're starting at the bottom of the tree, working our way up, making sure that everything, each node is the root of a heap as we go. So we did that with this node here by swapping the 10 and the 5. Now we're over to the 3. In order to make that into a heap, we're going to have to swap the 3 and the 9. So the swapping of the 3 and the 9 is what happens when we call heap rebuild. Okay, and so now we're all the way down to, in our for loop, we're all the way down to 0. We're down to the root. It's a 6. And so what we're going to have to do is reheapify that 6 down to wherever it belongs. And, you know, now things have changed enough that I can't do it without drawing a picture. So let's see if there's a picture. Here's the picture. Right, so here's the original array. Notice they don't even show heap rebuild of 5, 4, or 3 because those are just the leaves and they're already going to be heaps. Anyone want to ask a question? So this for loop here is going to go 2, 1, index is going to be 2, 1, 0, right? That's why it's saying heap rebuild 2, heap rebuild 1, heap rebuild 0. The argument represents the index of the node that we're going to be working on. So heap rebuild 2 causes the 5 and the 10 to get swapped, right? Because we are making the 5, the right subtree of the 6 there, into a heap. So we swap the 5 and the 10. Then when we call heap rebuild with the 9, actually, I guess we would be calling heap rebuild with the 3, because that's heap rebuild sub 1. And so we're going to have to swap 3 with its largest child. So we swap the 3 and the 9. And so that's how we get this picture. And so now if the, let me say this correctly, the heap whose root has index 1 is now a proper heap. I'm going to try one more time. The tree whose root has index 1 is now a heap. So back in this picture, the tree whose root had index 1, so in other words, this 3 here, was not a proper heap. So we reheapified it, so now it is a proper heap. And now we just have to do the same thing with index 0, which is the root now, right? So we're going to take the 6, swap it with its largest subchild, with its largest child. And so now the 6 is going to be down here to the right. So that operation is creating the heap, right? Taking an array that just has random numbers in it and making it into a heap. That is something that I want you to be able to do. Just, writing it out on a piece of paper. That's what this question 10 here is, and I'm going to assign that in the assignment. So this is for index gets n minus 1 down to 0, heap rebuild. That's exactly what we were doing up here, right? That's exactly just a copy of this for loop. So you're going to need to be able to do that. And that exact process is illustrated here in figure 17. Anyone want to ask a question? Okay. So the next section in the text is just showing how you would use a heap to implement a priority queue. There's really not much to that in terms of understanding heaps. It's just a lot of syntax, right? Because we're just building a class called priority queue on top of the heap. And most of the member functions are going to be defined just by a single function called to a heap member function. Right, so here we've got a constructor, and what it does is it calls the heap constructor. Here we've got a isEmpty function, and what it does is it calls the heap isEmpty function, and so on. So don't worry too much about this code. All right. I'm going to have you do assignment 11, but basically it's just, you don't even have to think about priority queues. It's just the same thing as it would be if this was a heap and we were adding a 5 to it, right? Okay, so we're done talking about heaps now, except we're going to talk about heap sort. And I'm not sure if you remember, but back when we talked about sorting, searching and sorting and efficiency, I gave you some code that was my own code that had a bunch of different sorts in it, and you could use it to time different things. So give me a second to just go there. Yeah, let me share this. Hold on. I'm going to new share. Let's share that. Okay, so lesson sorting lesson, sort.cpp. So hopefully you took a look at this. It'll look familiar. And Oh, I have these commented out. That's wrong. But anyway, so you can see there's insertion sort, merge sort, heap sort, and quick sort. And heap sort is going to be down here. So we'll come back and look at the code in a little bit. You're not responsible for the code for heap sort, but we may talk about it a little bit just because it's, as I keep saying, just because it's so. And you can see here, there's a function called reheapify down, and a function called, oh, there's not a function called reheapify up, because that's too simple. That's just this right here. Right, and convert to heap. Okay, so let me go back to talking about heap sort. So basically, the idea behind heap sort is step one, change the array into a heap. So that's what we were just talking about a minute ago, right? That the algorithm that I kind of went on and on about was taking an array with just random numbers in it, turning it into a heap. That is step one of heap sort. Okay. Then after you have a heap, what you're going to do is, so here's an array. You're going to take the largest item from the heap, swap it to the end of the portion of the array that is not yet sorted, and then reheapify what's left. So we, at any particular point during the execution of this algorithm, the array is going to have two parts. It's going to be the part that is still a heap, and it's going to be the part that already has the items sorted. Okay, so each step is going to be, let's see if this code helps or not. Well, actually, let's look at the picture. That'll be simpler. So this is assuming we've already turned it into a heap. Okay, hopefully you're really good by now at looking at this array and seeing how it matches with the tree over here. And I'm actually, I don't know if you've looked at the assignment yet, but I'm actually making you do this in excruciating detail. So there's not much to the assignment this week. There's no programming, but I did decide that it was important that you actually go through this process and show the steps in excruciating detail. So you're going to have to do this. So first step is to make the array into a heap. They haven't shown that here in your homework. You're going to have to show that part too. And then here's what happens. Move the 10 to the end. So swap the array sub 0 with array sub 5. So the last item in the part of the array that's still a heap. And then reheapify the 5 down. So swap the 5 and the 9. And now you've got a heap again, right? And so now you've got 5 items in your heap instead of 6, and the 10 is in the part of the array that's sorted. Okay, so next step, same thing again, swap the 9, which is going to be the largest item because it's at the root of the heap here. Swap the 9 with the last item that's still in the heap, which is the 2. So that's shown here. The 2 and the 9 are swapped. Now the 9 is part of the sorted list. And up here, I've got the heap, but it's not a heap. So I need to reheapify down to make it a heap. So I swap the 2 and the 6 because I look at the 2's 2 children, I figure out which one's larger, and I swap it with the larger of the 2 children. Okay, so that same process over and over again, right? Swap array sub 0 with the last item that's still in the heap. Move this bar over so that over from here to here, right? So that now that item that I just swapped to the end is part of the sorted part of the array. And the heap now just is the 3, 5, 2. And then reheapify down to make it back into a heap. Swap the 5 and the 2, move this bar over so that the 5 is now considered part of the sorted part of the array. I'm left with just 2, 3. I have to turn that back into a heap. So now it's 3, 2. Same thing again. Swap the first item in the heap with the last item in the heap. So I'm swapping the 3 and the 2, moving this bar over so that the 3 is now considered part of the sorted list. And then at this point, I only have one item in my heap, so I'm done. Okay. Turns out heap sort's pretty darn efficient. So any questions about that process?
Is there a difference between rebuild heap and heap rebuild, or is that a typo?
There is no difference. Oh yeah, interesting. I didn't catch that. That's a typo. I think this is the typo, right? I think it's heap rebuild everywhere else. Yeah. Okay, I hope it's not too confusing that he's calling it heap rebuild and I'm calling it reheapify down. I just think the reheapify down is more descriptive of what's actually going on.
It's all just one function though, right? Like,
yes, that's correct. Those are different names for the same function. Okay, so I could do an example with you. Thought there was a. Is there? I thought that somewhere there was an exercise. Oh, here it is. Okay, question 12. Trace the heap sort as it sorts the following array into ascending order. So this is going to be very similar to what we did back in the sorting lesson, except I'm actually going to require you to do this in more detail now. I'm going to require you to redraw everything every time there's a swap. Okay, so I'll go ahead and go through that with you with this list. And then in the assignment, I'll give you a different list of numbers to work with. I need to take like a 3-minute break here. And then I'm hoping this process will just take us, I'm usually wrong when I make these guesses, but hopefully it'll just take us a few minutes and we'll be pretty much done. So let me stop the recording here. Pause. Okay, so I just remembered that my plan was to have this diagram prepared in advance. And I didn't do that. So give me a second here. Okay, so here's what we're starting with. Here's the array, just random numbers in the array. This is the binary tree that would be the quote heap unquote that would be represented by this array. I guess what I should say is this is the complete binary tree that is represented by this array. So like we talked about, there's basically 2 steps. The first step is we need to make this thing into a heap. The way we do that is we, let me think about that for a sec. So we're going to take each item in the array, starting with the last one. And so we are going to start with the last node in the tree, and we're going to work our way up, making each node into a, I guess I should say each subtree into a heap as we go. So the 60 and the 40 and the 80, those are leaves that are already heaps. when we get to the 20, we're going to have to reheapify the 20 down. So we're going to swap the 20 and the 60. So I think I'm just going to copy this whole thing. Oop, that didn't work. Okay, so I'm swapping the 20 and the 60. Any questions about why the 20 and the 60? Okay, so 60 and 20 get swapped. And what that does in the picture is 60, 20. So that's the first step. So now the yikes, let's do that. Now the 60 is a heap, or the 60 is the root of a heap. So now we move over to the 30. The 30 is the subtree that is rooted by the 30 is not a heap, so we need to reheapify down. So we're going to swap the 30 with its largest child, which is the 80. So copy. We're swapping the 30 and the 80. And in the array, what that looks like is 30, 80. Okay, so now this node is a heap, the root of a heap. So now we're still working our way up one level at a time. So now we go up to the 25. So now this is not a heap, so we're going to have to reheapify the 25 down. The first step is going to be swap the 25 with its larger child, which is the 80. And do that in the array also. Whoops. Okay. And now the 25 is not a heap. So I have to continue my reheapify down. So I'm going to swap the 25 and the 40. So 40, 25, and the tree that is like this. And now we have a heap, right? So we are done with step one of the heap sort process, and that is turn the array into a heap. Any questions so far? Okay, so now what we're going to do is we're going to swap. It's always going to be array sub 0 with the last item that has not been sorted yet. So in this case, we're going to swap the 80 and the 20. Yeah. Swap the 80 and the 20. And then we sort of have a we have a bar here, sort of conceptually. I'm gonna color the part of the array that is sorted. I'm gonna color it yellow. Okay. And the way that that's gonna look in the picture is swap the 20 and the 80. And might as well color yellow there too. Okay, so just keep doing that. Swap the first item in the array with the last item in the part of the array that is still not so. Oh, actually, sorry, almost skipped the step. Now we have to turn this back into a heap again, right? But only the part of the tree that is not sorted. In fact, I can probably just get rid of this, but I'll leave it there. I'll color it yellow. So we need to reheapify the 20. So we're going to swap the 20 and the 60. Correct. Yes, that's right. When I say sort the array, what this is that this is just another technique for sorting along with quick sort or merge sort or selection sort, except the strategy is to use the concept of a heap to get the array sorted. Good question. Okay, so we need to reheapify this starting at the 20. So we're going to swap the 20 and the 60. Oops. Something really weird just happened. Let me try that again. Okay, got him a little too close, but it'll do. All right, so we're swapping the 20 and the 60 because 60 is 20's largest child. So swap the 20 and the 60. Okay, so now what's next? We're not going to swap the 20 and the 80 because the 80 is no longer considered part of the heap, right? The things that I have yellow here are no longer part of the heap. Another option would be to just delete them from this picture over here, but I think I'm just going to keep them in there, but turn them yellow. Okay, so now what we need to do is, so we've done recreating the heap, right? If you look at the part of this tree that is not yellow, it's a heap. So now we're back to the next round of swap array sub 0 with the last item that is still part of the heap. So swap the 25 and the 60. Over here, that looks like this. Okay, it's interesting. Parts of this algorithm are easier to see if you're looking at the array, like that thing I just did. Other parts are easier to see if you're looking at the tree. So that's kind of like why we like to have both versions up here. Okay, so we did that swap, and now we just need to change it back into a heap again. I'm having problems here. There we go. So now you can see that, well, first of all, I should make this yellow. That's now part of the sorted list. It's no longer part of the heap. But now the part of this tree that is not a heap is not, that is not sorted is no longer a heap. So we have to turn it into a heap. So we swap the 25 and the 40 because 40 is 25's largest child. And the way that looks over here is swapping the 25 and the 40. And it's still not a heap. I'm going to have to swap the 25 and the 30 now. So swap the 25 and the 30. Okay, now it's a heap. So the next step is going to be to swap array sub 0 with the last item in the array that is still part of the heap. So swap the 40 with the 25. Okay. Now the 40 is part of the sorted list and no longer part of the heap. Now we have to look at the rest of this remaining tree and turn it back into a heap. So that means swap 25 with its largest child, which is 30. So swap the 25 and the 30. Over here, that looks like that. Now we're back to having a heap up here. So we are back to the point where we can swap array sub 0 with the last item in the array that is still part of the heap. So swap the 30 and the 20. Okay. Now, and make the 30 yellow, because the yellow is now part of the sorted list and no longer part of the heap. Okay. The remaining heap is not a heap, so we need to reheapify down. So we swap 20 with its largest child, which is its only child, 25. So swap the 20 and the 25. It may seem a little weird to do that in the array because we see that it's already in the right order now, but there's no way for the heap sort algorithm to know that. So we just plow ahead, swap the 25 and the 20. So it's a heap again. Now it's back to being a heap. So we swap array sub 0 with the last item in the array that is still part of the heap. So the 20 and the 25. And so now the 25 is yellow. And now we look at our array and the there's only one item left in the heap, so we are done. Okay, so now you can look at this array and you can see that they are sorted. Any questions about all that? I know that seems extremely tedious. You know, I drew lots of pictures, but I think that going through that process a couple times, if you can get yourself to just sit down and do it, is going to be super helpful in just understanding how the whole thing works. Okay, if I were you, I would actually do this in Excel and just do it exactly the way I did with the copy and paste. That'd probably be the simplest way to do it. And then you can just submit an Excel file when you submit your assignment. Any questions about heap sort there? Yeah, that would make sense, especially the sorting. There's just a lot of details to keep track of, right? Okay. All right, so I want to take a look at the code again, just a little bit. We're almost done, but let's take a look. So here's the heap sort code. Hopefully you can see how this is fitting into the simulation we just did. The first step is just converting it to a heap, which is, it's a little set up a little differently than how I described it. But don't worry too much about that. Just keep in mind the way I simulated it anyway was start at the last node in the tree, make sure it's a heap, then go to the second to the last node in the tree, make sure that's a heap, and go to the third to last node in the tree, make sure that's a heap. Keep going like that until you get all the way to the first node in the tree and make sure that's a heap. So that's how you convert an array into a heap. And then while num unsorted is greater than 1, num unsorted minus minus. So that's sort of moving the bar to the left or moving the yellow portion further to the left. Swap list sub 0 with the last item in the list that is still in the heap, and then reheapify down. Okay, so that's what we did. And then the reheapify down is kind of complicated, but I don't want to worry too much about that. What I do want to do, I know you guys probably just want to go, but I'm super interested in just one time. I'm gonna put this into a file. And I just want to take a look at how long this is going to take. Let's see. So I've got the size of my array at 50,000 now. And so let's see how the speed of heap sort compares with the other heaps. Oh, I forgot that you guys couldn't see what I was doing. Sorry. Oh. Okay, so that whole time I was actually looking at the heap sort code and pointing at different parts of it. But hopefully it'll make sense if you go back and look over it a little bit. And I don't know, I'm being a little bit confusing, I suppose, when I say I'm not holding you responsible for the code, but then I end up talking a lot about it. I just think if I were you, I'd want to sit and stare at it for a while so I understand it, even though I'm telling you that I'm not going to test you on it or anything like that. Because it's pretty cool. Okay, so I've got sort.cpp there, and I'm going to run it. I fill the array. So now we are doing, I promise it won't take too long. We're doing bubble sort. Bubble took this many milliseconds, so about 12 seconds, right? The funny thing about this is that insertion, no, I think it's selection sort always goes way faster than it should. No idea why that is. Right, and then all of the log squared sorts took a while, right? And then the log in sorts were like pretty much instantaneous. But you can see that quick sort is still a lot faster than heap sort, but heap sort beats merge sort, at least on average. So heap sort is a log in log n, sorry. Heap sort is an in log in sort, just like merge sort and quick sort. Okay, anything else you want to talk about? I think I'm done, unless there are questions. Okay, I will get this posted as soon as I can. And let me know if you have any, if you get stuck on any of this. Okay.